Hello there and welcome to my new video. And this one, we're going to focus on the topic of CRISPR-Cas9 cuts and knockouts. And I know this may seem like an obvious topic, but in the course of attempting to carry out CRISPR-Cas9 knock-ins in fruit flies, we did encounter a few interesting phenomena which I think are worthy of note. So buckle up and bear with me on this one. First, here is the anatomy of a Cas9 cutting. This is the classic nuclease, and this is an illustration of the location of the guide RNA recognition in fruit flies. And here we have our PAM site, but more importantly, and yes, the term direction of munch is not a technical term. It is just my own expression that predominantly bases are lost in this direction. It's not exclusive, it's just a sort of a general thing. And yes, my pointer is still set on Woodstock mode. Point is that this area is going to be lost preferentially. So here are some potential examples of things you could get. You only lose like a base or two in that kind of a direction, or more bases can be lost. It is essentially random because the cells are desperately trying to undo the damage they just occurred. But at the same time, if they do too good a job, it's restored to its original awesomeness and then is promptly attacked again. So it is a nasty repetitive cycle that keeps on going until the guide RNA site is lost. And it can occur in all these different sizes. That's the important take-home message. So now with this detail in mind, because this is super important, is after all, as covered in one of my other videos, you introduce wobbles to guarantee that the guide RNA site is lost in your repair template. But also, when comparing your wobbled template to the wild type, you notice a difference in restriction sites, either intentionally or accidentally, that have been changed. And the relative position relative to this diagram does change how your knockout or knock-in is going to go. And I've given them different names based on their traits. So here is the first type, which I call the hair trigger. And its name is richly deserved because basically here we have in the diagram, the red X is the location of the restriction enzyme site that is removed by our interference, and we have the red dashes, which are our wobbles. But here is the problem, is that after all, like I said in the previous slide, any base loss will suddenly disrupt this precious restriction site. So when you're doing your RFLP analysis, you will accidentally be thinking, hey, I've got success, because the restriction enzyme site disappeared if we're dealing with restriction enzyme site loss. That's why the introduction is so important if you're being more thorough. And here's another illustration which is more sort of up close and personal. Here we have Echo R1, a classic restriction site. And in this case, the highlighted portion is the Echo R1 restriction site, but the pair of scissors in this case, okay, and I don't know what that was. Go away. Typical. Anyway, the point is the cut location straddles this EcoR1 site, and because the bases are lost in this inverted case this away, a single loss of a T or a C, there's no more restriction site, and therefore no cutting, hair trigger activation and detection, which the hair trigger isn't all bad because, after all, if you were trying to simply knock out a gene, then this is the really, really hypersensitive way of doing it. If you pick a guide RNA that has this restriction site straddling the cut site in this way, it means no matter what the damage, you'll see it. Perfect. But all too often, in fact, in our case as well, we were on our quest for knock-ins. We want to introduce precise, delicate mutations, not knocking out of genes. We're kind of fond of genes. And so here we have the second type, which I call non-fussy. The reason, will become obvious, I hope. The point is, in this case, the restriction site is, let's say, 6 bases away from the cut location. So the odds of a catastrophic loss and thereby triggering a false positive is a lot less. It's not zero, but it's a lot less. So there is still the chance that you would see false positives if you had forgotten your repair template and you were simply just chewing away at the DNA. So that's what non-fussy is all about. like I said, because we have the different location of the restriction site. But there is a third type, which has slightly, well, it has a different prognosis, and this is the classical, what I call fussy, because the restriction site in this case, clearly through aggressive wobbles introduced by me elsewhere, causes a loss of restriction site way over here, not only far from the cut site, but in the non-desirable direction. And that means the odds of false positive are so near zero as to make no difference. And you would think that's great, eliminate the false positives. But it's not all sunshine and rainbows. Let me show you. So here is the merits of all three on a single slide. Hair trigger, as I said before, very high risk of false positives. It's easy to see if you're on the right track, because when you're screening fruit flies, it's reassuring to let you know that there's gold in them hills. So that's ideal for knockouts. Non-fussy, in many ways, is the best of both worlds, because there's a moderate risk of false positives, which does encourage you. It suggests, hey, this particular fly F1 or whatever you call F0 generation, they are causing changes, and therefore maybe check further offspring. So that to me is a desirable scenario. Fussy is good because the stringency is crazy high, but at the same time you get no indication that you're on the right track. And that can be disheartening. So, yes, fussy is good if your guide RNA, by blind luck, is totally awesome. Yes, usually it is awesome, but you never can tell. Sometimes guide RNAs can be lame. So, if I had to pick for a knock-in, I would pick non-fussy. Call me old-fashioned. And if I go for knockouts, no question, hair trigger every day of the week and twice on Sunday. So, now, let's move on to a focused example of hair trigger knockouts. When we were actually innocently trying to introduce a mutation in fruit flies, we had this situation. So there we were, innocently trying to introduce this already published mutation, but because the restriction site that we were using was terribly close to this neighborhood, it caused us to, unfortunately, grab a few guys that were in fact false positives. And this caused extra complications, because here we have the wild type chromas, which we would always include, and the red line denotes where the cut site is. If you look very closely, you can see actually some bases were lost here and here. But, hindsight is 2020. I know it because these guys, anyway, point is, Chroma is great, but the software just completely falls to bits because you're effectively listening to two different voices at the same time. And with 4 different colors on top of that, it just becomes jumble. And how on earth are you going to comprehend that? Well, I am so glad you asked, because I came up with an approach which I affectionately call the drumbeat maneuver, or the drumbeat method. Point is, drumbeat. Why do I call it a drumbeat? Because after all, think of the 4 DNA bases like 4 instruments on a music track. And in this case, the red, or T, is the drums. So if you take away all the other instruments and only listen to the drums, then stuff changes to this. So here we have the normal rhythm before, which matches for everyone, duh. But here we have, all you're hearing is dum, 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 da da dum, da da dum, dum. But if you were to listen to 2 slightly out of phase recordings of that same track, here is where it gets educational. So in this case down here, we actually lost 2 nucleotides. So that single drum beat, as well as still being there, hey, we get 2 seconds early, or 2 bases early, and this dum, dum becomes dum, dum, dum. So that also corroborates what you're seeing. Similarly, here we have, the single drum beat there. Hey, it's pushed over there. But that triplet, because it's moved by 2, you get a quintuplet instead. Hey, good use of the word quintuplet. Possibly my first ever. Point is, and down lower here, we have only 1 base loss. Why am I obsessed with 1 or 2? Because if it's a multiple of 3, your frame can survive, and therefore the gene may survive, which isn't good. If you want to do a knockout, it better be dead, as in frame lost. So yes, on the bottom one, every single beat, so your dum space dum becomes quadruplet. Single becomes doublet. You get the idea. And so This, I only chose an easy example because trust me, this is not the nastiest I've seen. This is the nicest. I've seen one where it was 16 bases losses, which did require a lot of deep thought and thinking about drums to solve. But also, if you have a hunch this is what the knockout is, then you can also, because this is Drumbeat in red, switch to Drumbeat in blue. So yeah, okay, because blue or C is more popular, you have every single isolated peak. Hey, loss of a single base becomes a doublet, while in this, because you have a two base gap, two distant guys becomes four distant guys. You get the idea. So this is an easy way to basically diagnose a heterozygote even before you get them to homozygosity. So in our lucky case, this gene was actually survivable if you're knocked out. This isn't always the case. In fact, all too often it isn't the case. But this is a way of being sure of what on earth you're dealing with. And in theory, if you were, say, doing a knockout attempt on a cell line, you could still apply the Drumbeat method to loss in more than one copy. You just have to have a wild type version of the chroma up top, and then, yes, compare it down low to a jumbled version. In this case where cell lines have 3 or 4 copies of the chromosomes, I don't envy you. Personally, I would avoid trying the Drumbeat on that. But hey, you do you. But anyway, that is enough for me from me. That's enough for me for now. And just want to say thank you for watching, and don't forget to like and subscribe. Any video ideas you have, feel free to share them with the rest of the group, and feel free to comment. Thank you very much.